I'm Chris Anderson. I research spin and thermal transport in this laboratory at the University of Manchester. I'm going to talk about how spin transport might enable the development of computers in the future. But to start with, let's consider what a computer is. It's usually considered to be an electronic device. However, it doesn't have to be. Some of the earlier computers were very mechanical. It usually stores, retrieves and processes information. But if we poke down further inside the computer, what do we find? Well, we find circuit boards, we find wires, and we find chips. Chips, as we know, can take many forms. They can be memory, they can be processors. But what does a chip do? And what's in it? Well, it manipulates and stores ones and zeros as voltages. And it also contains switches, which is what does the processing. So transistors are used as switches in computers. How big is a transistor? Well, when the transistor was invented mid last century, it was about 3 centimeters high. A single one was about 3 centimeters high. It was invented at the Bell Labs in New York City, and eventually the people who invented it won the Nobel Prize. At the end of the 1940s, the first stored program computer was invented here at Manchester University, along with Ferranti, and that used valves as their switches to do this processing. They were huge as well, and in fact the computer took up a whole room. Nowadays we make transistors on chips, and these transistors are as small as tens of nanometers. Well, how big is a nanometer? Well, it's 1,000th of a micrometer, or a micron as we call it. It's 1,000,000th of a millimeter. So they're really tiny, which means that we can fit billions of them on a chip. Over the last 50 years, Moore's law has been a good guide to us. It tells us that the number of transistors on a chip doubles roughly every 1.5 years. It also tells us that the processing power of a computer will double roughly every 1.5 years. But Moore's law, we believe, is coming to an end. And one of the reasons for that is that these transistors require energy. We need to apply energy to switch from a 1 to a 0, to change the voltage state of these transistors. That means that the energy has to be dissipated in the transistor somewhere as heat. And it's very difficult to get the heat out. Wouldn't it be better then if we didn't put the energy in the first place and we could find another way of switching? One possible way is through the use of Spintronics. The word Spintronics is a portmanteau of the words spin, transport, electronics. In Spintronics, instead of using the charge of an electron travelling through the wires or the transistors, we use another property of the electron called its spin. We think of spin like a spinning top. However, that's just a model for physicists and engineers to think about it. The spin of an electron is a quantum property, which means that if we measure it, we either see it as spin up or spin down. In other words, which way it's rotating. We can quite easily imagine that we can use these two states as 1 and 0, or 0 and 1, doesn't matter which way round. It turns out that graphene, amongst all its other superlative properties, is absolutely great at transporting spins. We just need to then find a way of controlling those spins as they travel in the graphene. And this is what we use the spin transistor for. So our measurements in here are looking at how we can transport the spins in graphene, but at the same time control them. We put our special graphene devices in a fire stack here, where we can create a vacuum. We can take the temperature down to 20 Kelvin or less, and we can sweep a magnetic field and apply that at any angle by rotating on this table here. Let's have a look at the two basic measurements that we make in this lab. Firstly, we inject electrons with a particular spin into our graphene channel and watch how the spin decays as it moves along the channel, as it diffuses along the channel. Then we apply a magnetic field vertically through the graphene channel. This causes the electrons to precess, and what that is when the electron wobbles on its axis like this. The higher the magnetic field, the more it'll wobble, or the faster it will wobble. Once we've established these measurements for the device, we can then start using other features of the architecture to create a spin transistor. We're working hard on understanding the physics of spin transport in our graphene heterostructures, our devices. The whole field of spintronics is much wider than what we've shown you here. We could make other components such as spin diodes and spin oscillators, and also read-write heads for hard disks have been made using spin technology. We create ultra-sensitive magnetic sensors, and in the mid-2000s this was applied to hard disks, and that's what caused the sudden increase up to terabytes of storage. Spintronics can also be used to produce non-volatile memory for computers. This usually is called magnetic random access memory. For return to the premise of this talk, that we want to make transistors that are less power hungry, because the size of them is limited by the energy dissipation, in other words getting the heat out of the chip. Spin gives us the potential to be able to do that, because it takes a lot less energy to flip the spin from up to down or from 1 to 0. So we're working hard on the understanding of spin transport and spin control in this lab. So in the future, Spintronics can become an enabling technology for not only classical computers, but potentially for quantum computers as well. Thanks for listening. I hope what you've heard inspires you to carry out research into this really interesting area of physics that's graphene spintronics.